what I'm going to show you starting out is going from a power flow case to a dynamics model. So what we're going to go through in this section is the basics of doing a transient stability run, but then mostly focusing on how do you see data that's available in an existing case, and how does Power World help you in dealing with this data. Our design philosophy in Power World is to make power system analysis as easy as possible, but that is not saying it's easy. Okay, so I mean, we need, obviously smart engineers. So we're going to try to reduce the barrier or the entry barrier to doing this and make it kind of fun. But as you start dealing with models like the WCC, there's a lot of data out there. So to get us going, I thought we'd just start out with a 7-bus case that I created way early on in the history of Power World and had no idea that we'd be still using it 20 years later. But if you can open up that case, the B7 flat case, that has no power system or transient stability information in it. So I'm going to open up B7 flat. This is a 7-bus power flow case. If you go and look at add-ons, so if you click on add-ons, that's how we're going to get access to transient stability. And then over here, under the stability case info, if you go down and look at models in use, it shows you how many models are defined for this case, and the answer is none. So we're going to create a transient stability simulation from just a power flow case in just a few seconds here. Okay, so I'm going to go back to, I'm going to close this by clicking on this little arrow, go back to my one-line diagram, and I'm going to quickly, and you can too, put in generator models for just 2 of our generators. So this is just motivational. We'll get to the details later on. So if you go to the generator in the upper left part of the display, it's 1, and you right-click on that generator, you get a generator information dialog, which is where we show all our power flow information. So it's generator information for current case. If you've used Power World for the power flow, this is where you see the megawatt output, the max, min, stuff like that. If you go on the tabs here, power and voltage control, OPF, faults, owners, and go all the way over to the right, there's one called stability. That's where we're going to show you what stability models are represented for these generators. Okay, so right-click on the generator. I did generator 1. Go to stability. Then you'll see some sub-models or sub-tabs here, machine models, exciters, governors, stabilizers. There's nothing in here. We're going to just insert a machine model. So just click on that insert button under machine models, and it'll give you a list of models to put in. We're just going to put in a Gen ROU, which is just a type of generator. Just highlight Gen ROU and click OK, and it'll put in a generator model. Okay, the parameters matter, but we're going to ignore them for right now. This is just to get you going. So just click OK, and you added a model for generator at bus 1. Go down to the generator at bus 7. Really doesn't matter which other generator you pick, and do the same thing. So I just want to get 2 dynamic models in my case. So I do generator information dialog. I go to the stability tab, and I insert. I'm going to put in a Gen ROU, and again, just take the default values on it and click OK. You could put in more, but if you have 2, that's good.
So built in, you've got defaults for all of these models.
Yeah, we've got defaults for all the models. Obviously, in representing a real system, you don't want to use the defaults because they are default. Okay, but they give you a feel for what should be there, more for students than anything else. But if you're playing around with a new model and you want to say, hey, I wonder how this responds, at least you have parameters to start with. Okay, so now we're going to go and do a transient stability run. So if you click on add-ons, again on the top, you'll see transient stability. That opens up, if you click on that, that opens up the main transient stability form. Okay, so add-ons, click on transient stability. That's going to be our main screen, and we'll be talking about that screen a lot over the course of the days. If you do a transient stability run, it's going to be a time domain simulation. So you have a start time, an end time, and a time step. We don't care about the values there right now, just whatever the defaults are. But we want to store some results. PowerWorld lets you have a lot of control over which results you want to store. So we're going to just tell it very quickly now to store some results. So if you go on the left side, there's a button called Result Storage, way over on the left. If you click on that, you go to the page that tells you what data you want to store. And there's a lot of stuff you can store. Do you guys see, if you're on this page, do you see for the generator, save rotor angle? Everybody see that column? Yeah. We'll just click save rotor angle, and I just click the first entry 1 to yes. And then if you want to grab that little square and pull it down, you can set them all to yes. Really doesn't matter how many you save, just so you're saving something. Okay? So just save some rotor angles. I've got them all saved. Okay, so now we put in 2 models. We're saving rotor angles. If we go up to simulation here, so go over to the left side and click on simulation, this just goes back to the main page that we started with. And then I want you to do a transient stability run, and all you have to do is click Run Transient Stability, which is the button right up here on the left side of the form, almost towards the top. Do Run Transient Stability. Oops, I need to change my time step. Do you guys have for a time step 0.02 seconds? Let's set that to, we'll use cycles. So if you click the cycles, let's set that to 0.25 cycles. Under the simulation for time step, so it's right underneath the end time, click on the specified time step in cycles and set it to 0.25. So we're going to run a quarter cycle. This is the delta T that I was talking about. It gave us some error violations because the default parameters don't work with a 0.02's time step. Okay, and the new version, we've changed that default. It should be much shorter now. 0.02 is too long a default value. Okay, then click Run Transient Stability, and it should do a run, and then it'll say finished at 10 seconds. So now we did a transient stability run. We ran it out 10 seconds. You want to see what are your results. So the result storage is on the left. That's where you specify what you want to store. Then if you go below it, results from RAM shows you the results that were stored in RAM. And as we'll talk about later on today, you can store results directly to a hard drive, or you can store them in RAM. You'd want to store them in RAM if you want to see them. Okay, I've got results in generator 1 and results for generator 7. The reason why you don't have any results for generator 2, 4, and 6 is we didn't put any models for them. Okay, this shows you the time domain results. So if you scroll down on the bar, time is in the second column there. It's giving you results for 0 to 10 seconds at each time step. I like to use the quick plotting capability to see the results. So if you right-click on that column, like I'm looking at generator 1 rotor angle, I right-click on it and I do plot column. I see a plot result there, and it looks rather dramatic, waves up and down. But the value, if you look at the value range there, that value is not changing at all. It's constant. Change the color. This is a default simple tool, and we're going to talk a lot about how to do pretty plots. This is just a quick and dirty plot. That's the result. That's showing the rotor angle over 10 seconds. You might say, that's really bizarre. The problem, though, is with the default plot is its time, or its Y value is essentially not changing at all. Okay, the scale on this is like a 100,000th of a degree. So it's flat. Nothing's going on. So we just did a transient stability run, and the angle stayed constant because we didn't put any disturbance on our system. So what we're going to do now is put a disturbance on the system. So what we're going to do is just put a fault on the system. So I'm going to close the plot, and we go back up to our simulation main page, and the next thing we're going to do is insert a transient contingency. So if you see on the main page right here, there's a button called Insert, Apply, and Clear Fault. We're going to do a real simple disturbance. All we're going to do is put a fault at some bus. So just click that button there, Insert and Apply, Clear Fault. And it brings up a dialog. It's the Transient Stability Contingency Element dialog. It's letting you put in a fault at one bus in the system or any bus you want. We'll just put the default, which is bus 1. We're going to apply a fault. We're going to put it on at time t equals 1, and we're going to clear it at time t equals 1.1 seconds. So all you have to do is click OK. Well, you could specify it in cycles, but this one's just in seconds. Okay, it shows you the event that's defined down here, which we'll talk about later on. So all this is going to be covered later on. This is just a motivational example. Okay, then click Run Transient Stability right here, and you should run it. And it should run for, again, 10 seconds. And if you look at now your results from RAM again over here, and then I look at my results here, and I'm going to do the quick plot again. Plot column. And there's your rotor angle on your system. In essence, we covered the main parts of transient stability right there. You start out with a power flow, which is where we started out. We need to define some models. We need to define what we want to store. We need to define a contingency. We run it. We look at the results, and that's that. The idea is we tried to make it simple for people to get started in doing this so you can play around with it.
Guys, I'm assuming, Tom, of course, we have a lot of RAS out here, of course, so same dialogue we used to do, GenDraw, the reactive switching, that sort of stuff, the same basic.
Yeah, it's the idea is we've leveraged what we have in Power World for power flow to use in transient stability. So getting into all the different contingencies and models and things like that, that's what we're going to cover for the rest of the time. But if you understand this example, this is the basics of what we're talking about. So I wanted to get through it so you see sort of the basics of how you do it. You start with a power flow, then you throw transient stability models on top of it. You have to define what you want to store, and we've got it so you can store everything if you want. The problem is that right now Power World is 32 bits, and 32 bits only gives us 4 gigabytes of storage. And if you do a 30-second study and you're storing everything every time step and you do the math, you get a lot of data really fast. So we provide ways to specify what you want to store, and then there's going to be a lot on how do you look at results, how do you do mini runs if you don't just want to do run, all the complications. But the starting point is rather simple.
Are you guys going to transition to 64-bit?
Yeah, we're working on that right now.
Okay.
The new compiler supports it, and we're just working on the newer code to do it.
Is there a way to edit the time steps and cycles? I mean, the sequence of events and cycles, instead of having to put 1.1 clear default, maybe I want to put 6. I see the cycles are displayed. Like it says 1.1 seconds is 6 cycles later, but...
yeah, you can insert stuff in cycles. That's helpful, particularly if you're a student or you're wanting to understand how to use transient stability. Small cases help all the time. But what you're about working for BPA is going to be using existing models, and you're going to have to interact with existing models that will have thousands of different models in them, many with all sorts of different parameters. You're not building a case from scratch like we did here. So how do you add this in? Well, Power World supports a number of different file formats for importing data. We have our own file format called the Power World Auxiliary format, which allows you to enter data on just about anything in. Then there are particular formats like PSLF has a DYD file that's used to bring in dynamics data. Power World can then read and write these formats and store data back in a number of different formats as well. So we're going to look at an older WCC model in just a second and show you how you can load that in. The way we've set up Simulator is to give you a number of different ways to get access to saving and loading data and actually doing a lot of different things. One way to load in data is if you go to the File menu, you'll see File, you'll see lots of options for opening a new case, opening a case, saving a case. If you go down here, we're going to eventually get to loading transient stability data, and I don't think we do it in this one right now, but you can also save transient stability data. So we'll get to that in just a second. Then there's the auxiliary file format. We talk about that in another training course that we're not going to get through today, in this course, but we will show you how to use aux files to save a whole bunch of different things associated with transient stability. For example, let's say you define a whole set of plots that you like to show the WCC model with your own particular plots. You load a new case in. How do you get access to your customized plots? We'll show you that you can save them in an aux file and load them in to any other case, and it makes it really simple to do. Okay, so we're going to get through the details on, right in this one, how do you get access to all different sorts of information about your case. So Power World provides you a way to see a lot of data associated with your case, and we're going to go through the details of that in just a second. So let's start out by going into Simulator, and we're going to go File, Open Case. We've got the 7-bus case in there right now, and we're going to just write over that. Okay, if you get to the Open dialog, normally you would load in a Power World PWB, which is what we did with B7 flat. We're going to start out with loading in a case in the PSLF EPC format. So if you go down here for the format, it says Power World Binary. If you click on the arrow there, you will see the EPC option. Just do the GEEPC format without options. So the first one there. There's only one EPC file. That's the West Example EPC. So go ahead and load that in. That's an older WECC case, pretty good sized case, 14 megabyte. Yeah, it should be the only one in the directory. You need to have the GEEPC format selected over here. It's in the same directory that the B7 flat was in.
West example. No, it's one.
Oh, is it? Oh, is it one deeper?
Yeah.
B7 flat lives in a lot of different areas because we use it so much. If you've got to it, just got to click on the name first, West Example, then click Open. Don't worry about saving your existing case. Just click No. That loads up a PowerFlow case in text format. Okay, so you should have a PowerFlow in there. You don't need to save it. I mean, you don't need to solve it. What we're going to do next is we're going to load in transient stability data. So we just loaded a PowerFlow case with no transient stability data. The way most of the data formats are is they have PowerFlow formats in one file, dynamics data in another file. For PSLF, this is in a DYD file. So what we're going to do is we're going to load West Example DYD. So we're going to augment our PowerFlow case with the dynamics data. So the question is, how do you do that? Oops. One way to do it is to go File, where we were at before. Rather than Open Case, now we're going to go down to Load Transient Stability Data. So in the File menu, I went down to Load Transient Stability Data. This allows you to load transient stability data in different formats. We're going to pick the DYD data format. So if you go over the Load DYD, it'll open up that dialog again. It's in the same directory as the EPC file was there. There should be just one example, westexample.dyd. Select that and open it. Okay, if you could go up, right up here on this icon, that's, I don't know, it's 1, 2, 3, 4, 5 icons, and it's the log icon. Open up the log if it's not open already. You should have message log. When you open a case, there's a lot of stuff that gets written into the message log, most of which you can ignore. But some of it is important. One issue, and this is covered in the slides, is there's a difference often between how generators are modeled in the PowerFlow and how they're modeled in Dynamics, particularly associated with generators that have a high-pressure steam model and a low-pressure steam model. In the PowerFlow, these units tend to be modeled as one generator. In transient stability, oftentimes they're modeled as two generators. So we loaded a PowerFlow model that, in this case, it would be at bus 14914. If you look at that case right when you load the PowerFlow model, there's just one generator model there. But in the dynamics data, there's going to be two actual models for generators there. What simulator does is it knows about this. It knows that, hey, we have to split that generator up, and we split it up. It's known as a cross-compound unit, and represent it now as two generators, and then we log it that occurred. That takes place transparently. You don't have to be concerned about it, but it's something to just know about.
So there's going to be two generators internally. There's not going to actually put two generator units.
No, it actually does.
It actually does.
You don't want to save it and compare it to your original power flow because it has changed the power flow.
Yeah, there's now two generators at that bus. It split it.
Well, and those, Tom, and physically usually those are actually physical separate units, is that not correct? It's cross-compound?
Yeah, it's a cross-compound unit. So, I mean, in essence, it's giving you a better model of what's really out there.
Power flow has it as one, and then simulator knows it's cross compounds because of GENCC and the dynamics data, and then it's creating another one.
Which is in fact the true physical case, two separate machines.
Right.
Yeah, it's two physical machines. So in essence, to do transient stability, we have to treat it as two physical machines. Power flow, it's okay. You can combine it in power flow, but in transient stability, it's two separate machines. Okay, so we loaded that example. We talked about the true separate machines. There's a lot of information in that DYD file, and we're going to see it in just a second. Okay, but the cross-compound units are something to be aware of. Okay, and there's actually data in the dynamics data that says kind of how they should be split. We talked about the informational messages. Now we're going to get into the Model Explorer.